Our final lesson in Chapter 2A, 2.3, Analyzing Graphs of Functions. We're going to look at things like vertical line test, finding zeros, looking at intervals over which functions increase and decrease, and then we'll maybe identify even and odd functions. I think we may cut that one out. We'll see. It'll be a fun surprise. If we look at a graph, look and kind of describe domain and range. Domain is always going to be determined on a graph from left to right, and that would be on the x-axis. Range goes from bottom to top, and that's on the y-axis. As long as you go in that order, so it's really from smallest to biggest for both of those, you'll be in great shape identifying domain and range. And for both of these, we'll use interval notation. And that's where we use brackets and parentheses as needed. When you're asked to evaluate f of x, go to the x-coordinate on the graph, and it's whatever this number is, and determine the y value. And that would be evaluating. Your answer would be represented like an ordered pair. For example, -1, 4. If you're asked to determine zeros, make sure to look for where the graph crosses the x-axis. And your answer will be x equals some number, and that's a zero of the function. All right, let's put all of this to the test. We've got domain and range, some evaluating, and finding zeros for the graph of f on the left. Notice we have domain and range first for A and B. When you're asked to find domain, remember we're going to go from left to right. So on that left-hand side, notice it starts at that location, and the x value is -1. And the graph goes all the way over to the right to this location here, where the x value equals 5. So the numbers start at -1 on the x-axis and go all the way over to 5. Now look at the types of dots we're kind of comparing to figure out our interval notation. The dot on the left is a closed dot. That means -1 gets a bracket because it equals -1 on the x-axis. The 5 on the right has an open dot, and because of that, we'll use a parenthesis to represent that boundary. That means it gets infinitely close to 5 but doesn't actually equal 5 for the input value. And that's how you find domain. You just literally read the graph from left to right. The range is going to start at the bottom and go to the top. So notice the smallest output value on the graph is down here when y equals -3, and it has a closed dot. You have to actually physically see an open dot, otherwise it'll always be a bracket. As we move up on the y-axis, the highest point is here at +3. And again, that's a closed dot. If we state our range from smallest to greatest, or least to greatest, it would go from -3 on the y-axis up to +3. It can equal -3, that gets a bracket. It can also equal +3 towards the top. That one also gets a bracket. So once you figure out your domain and your range, we can now do some evaluating. There we go, start with a clean slate here. Find f of -1. If we look at the definition, that means I'm going to go to -1 on the x-axis and determine where my output is. So I'll write f of -1 equals. If I go to -1 and find where the graph is, I have an output of +1. And you guys, that's literally the answer. It's that easy. Now let's try the next one, f of 2. Go to 2 on the x-axis and find where that point is. The output is -3. You can evaluate really quickly on a coordinate system with a graph already given just by following those rules. Find where the x value is and then determine the output on the graph itself. To find the zeros of the function, a zero is where it crosses the x-axis. So let's just add that in again, where it crosses the x-axis. And are there any zeros for this graph? I see a couple, From left to right, I see it crosses the x-axis right here when x equals 1. So we can either say x equals 1, or you can write it as an ordered pair, 1, 0. Keep moving along and notice it crosses the x-axis again at 4. So we would say x equals 4, or write the ordered pair 4, 0. We're just interpreting a graph for unique values like domain, range, evaluating function inputs, and finding zeros. Some of you may remember the vertical line test from Algebra 2. This is a quick test if a graph is already shown to determine whether or not it represents a function. Here's the definition. A set of all points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. So here's what you're looking for. Given that first graph on the left, if you draw a vertical line, notice it only intersects that graph at one location. No matter how many vertical lines we draw, it only intersects at most one time. Since it never crosses through the graph itself more than once, we would say that this is defined as a function. So it says use the vertical line test to determine whether or not the graph represents y as a function of x. It does. Oops, yes, it does. Well, let's just try that all over again. We would say, yes, it does. And why? Because it passes the vertical line test. And we'll just call it VLT for short. The circle in the next example is a graph, definitely, but it does not pass the vertical line test. Watch what happens here when we draw a vertical line, or mostly vertical. It intersects the circle on the top and the bottom. Since it intersects more than once, this is not represented as a function. That last one would be an example of a piecewise function. Remember when we evaluated piecewise functions in 2.2? This is a graph of what a piecewise defined function might look like. And if we draw vertical lines through the left, through the right, notice it only crosses at most one time. So yes, it is a function. And how do we know? It passes the vertical line test. Then we'll throw the V there. There we go. We're good to go. When you're asked to find zeros of a function, we've done this before. All you do is you set your equation equal to 0 and solve. So there's nothing new here. We've done this with linear and we've done this with quadratics. No matter what type of polynomial function or equation you're given, you can find zeros by applying this rule. For 3x squared plus x minus 10 equals 0, you could factor or do quadratic formula. If you factor this one, you would get x plus 2 times 3x minus 5. And we've practiced factoring before, so you can do that on your own if you'd like. Now remember, it does say it's equal to 0, so we would apply the zero product property. If we set x plus 2 equal to 0, we would get x equals negative 2. If we set 3x minus 5 equal to 0, we would get x equals positive 5/3 if we solved. So there are two zeros for that quadratic function. But now these following equations are a little bit unique. They're not exactly like functions we've seen before, or that we've worked with extensively in this class. G of x looks like a square root function, but it has an x squared in it. So let's see what we can do to find where this might possibly cross the x-axis. If we set it equal to 0 and try to solve for x, the first thing you'd want to do is square each side. And that would get rid of the square root. Well, when that happens, the square root cancels with that squared, but we still have 10 minus x squared left over on that side. And on the right, 0 squared stays 0, so nothing really changed there. Now to get x by itself, we're going to have to move 10 over. And we have negative x squared equals negative 10. We need to divide by negative 1, to get x by itself, and that would give us x squared equals 10. To get x by itself, the opposite now of squaring a number would be to take the square root. So now we have to think back to when we solved quadratics and what happened when we took the square root of two sides of an equation. We need to make sure to include that plus or minus out in front, and then try to simplify the square root if possible. Well, the only factors of 10 are 1 and 10 or 2 and 5. Because of that, it's already simplified. And notice we have two solutions or two zeros of the function. Our last example is a rational example. And if we set this equal to 0, we first have to recognize what t can't equal. We know that because of the denominator has to be not equal to 0. So t can't equal negative 5. That's just something that we have to verify with our final answer. But now for the work for the 0 itself. If we set the equation equal to 0, I'm going to make the right side an equation, or excuse me, a fraction as well. If we have a fraction on the left, I'll put a fraction on the right just simply by dividing 0 by 1. 0 divided by anything is 0. If you have a fraction on the left and the fraction on the right of an equation, we're going to cross multiply. I'll take 1 times 2t minus 3 and 0 times t plus 5. And the reason we do this is now we have 2t minus 3 on the left. 0 times anything is just 0 on the right. To solve, I would add 3, and that would give me 2t equals positive 3. And then divide both sides by 2. And we have one intercept, or one zero of the function at 3/2. Whoops, that's a 2 in there. Let's make sure you can see that. So make sure that when you're solving, you're recognizing each unique function has a different set of possible solutions. We're going to continue right on with 2.3 day 2 as there isn't much left for this lesson. And I'm not quite sure why my format is different from the template of notes, so sorry about that, but we'll make sure we're all on the same page when we're done. It says using interval notation to describe increasing, decreasing, and constant type functions. When we do this, we're only going to look at x values. So we're only going to go left to right. Make sure to write this down. So we'll go from left to right. So looking at that picture, again, we're going to make sure we read the graph from left to right. I guess we're going to be really consistent on that. I should have had them both on the same page. A graph is decreasing from left to right from -2 on the x-axis to 0. So notice that represents that decreasing amount from left to right. And we'll always use just parentheses to describe increasing, decreasing, and constant behavior. So only parentheses, no brackets. So it doesn't matter if you can equal it or not. The boundary is just on the x value set. A constant is when it goes straight across. So there's no slope. A slope would be 0. Notice it goes straight across from left to right on the x-axis starting at 0 and ending at +2. And then the graph kind of curves up, but that would be considered increasing. So from left to right, the graph increases. And that would be on the x-axis starting at 2 and ending at 4. And again, only use parentheses to describe increasing, decreasing, and constant behavior. In the 3 graphs at the bottom, it says determine with open intervals on which each function is increasing, decreasing, or constant. So we're just going to apply those 3 examples those 3 terms with these examples at the bottom. For all 3 of them, would you please add arrows at the edges on the left and the right-hand side? For some reason, we didn't have them in the initial video template, so make sure to add those in, and then we'll walk through increasing, decreasing, and constant. And our rule to follow, remember everybody, start on the left-hand side, and then look for turning points. Does it actually change direction? So here's what I mean by that. In our first picture, on the left-hand side, we see that arrow towards the bottom. That means it's going towards negative infinity. So we're going to go ahead and write that in down here, negative infinity. But then as it goes to the right, it's going up until it reaches an x value of -1. So from left to right, between negative infinity and -1, the graph is increasing. And then at -1, that's a turning point. Now the graph changes direction. So now from here, it drops back down until it reaches an x value of +1. That means between -1 and +1, since the graph has a negative slope, it would be decreasing. And then that at 1, that's another turning point. So now notice at 1, the graph goes back up again, and it goes back up forever and ever and ever. That means from 1 to positive infinity, since it keeps going on the x-axis, the graph is increasing again. So at no time was there a constant. It was just increasing, then it decreased, then it increased again. See if you can try the next example. From left to right, see if you can determine when it's increasing, decreasing, or constant. And then press play and see how you did. Again, the key on these is to start on the left-hand side and go towards the right-hand side. With those arrows, that means it's going towards negative infinity on the left. But as you move to the right, it increases all the way till x equals 0. So from negative infinity to 0, the graph is increasing. And then it just simply goes straight across. From 0 to 2 on the x-axis, it's a constant. It has the same output values each time. At 2, as it goes towards positive infinity on the x-axis, the graph starts to decrease. This equation, or this graph, had an example of all three terms with open intervals. Let's try one more. The unique thing about our last graph is notice from left to right, as we continue that kind of pattern in our description, we have that negative infinity on the left. As you go to the right, it's increasing. But notice it's still increasing and still increasing. So even though the slope might change a little bit, it's increasing from left to right the entire time. That would indicate from negative infinity to positive infinity, the graph increases the entire time. We wouldn't break apart where it increases since there isn't an actual turning point in the shape of the graph. And that, everybody, is lesson 2.3.